Okay, so information. What is information? So information is knowledge that gets communicated in a certain context. In other words, if I just handed you a bunch of random bits, you wouldn't know what to do with you. But if I told you it was a PDF file or an MP3 or an ASCII file or whatever, now in that sort of context, you would be able to interpret those bits in a way that would actually let you access the knowledge that they contained. Okay, so there's a notion in which information resolves uncertainty. If you already sort of know it, if I give you some more bits, I haven't actually really transmitted any information. I've certainly given you some extra bits, but there's no increase in your knowledge, right? So what we're going to do when we're thinking about information is we're going to say, how much uncertainty did that digital message that just arrived, how much uncertainty did that resolve? So there's going to be this sort of connection between information, okay, and uncertainty. And we'll think of these as there's some. The more, as proportional, we'll think of, so the more uncertainty there is, probably the more information I'm going to have to give you to sort of resolve that. So this is going to be, this sort of insight, or this, if you will, definition, is going to be our way of coming up with a way of measuring the amount of information. What we really need to do is to measure the amount of uncertainty that was resolved by the arrival of this message, and then we'll be able to tell you how much information you got. Okay, so here's just a tiniest little bit of mathematics. Suppose I'm going to set up a sort of a slightly mathematical formulation of the problem that we're talking about. So I have some unknown quantity, represented in this case by a random variable. It's a discrete random variable. It can take on one of n different values. So I'm pulling cards from a deck. There's one of 52 possible choices. Okay, and then I can associate a probability with each of those choices. In the case of a 52-card deck, the chances of drawing a particular card is presumably 1 over 52. Or the chances of drawing a club is 1 over 13. 13 of the cards in that deck belong to the suit of clubs. Okay, so the way we're going to define the information content is we're going to say 1 over the probability. So that's basically a measure of the uncertainty. So this is inversely proportional to 1 over the probability of the event happening. And the way we're going to turn it into a metric, into a measure, is to take the log base 2 of that. And you can think of that as sort of a way of saying, how many bits would it take to encode the choices? And then I'm going to send you a message of that number of bits. So suppose I had 8 choices. How many bits does it take to represent one of 8 possible choices? Well, my representation has to be able to deal with any of the 8 choices, so I have to have 8 different things I can send you as part of my message. And I can do that in 3 bits. So if you consider about all the different combinations of 3 bits, so I can start off with 0, 0, 0, all the way through 1, 1, 1, there's 8 such combinations. So using 3 bits, 3 zeros or 1s, I can basically identify which of the 8 possible choices are available. So we're going to talk about the information about learning about a choice is equal to the log base 2 of 1 over the probability of that choice happening. And the base 2 comes from the fact that we're sort of using binary as our measure. The measure of the basic measure of information is the bit. Okay, and so what Claude Shannon did, he was sort of the father of information theory, was to define this notion of information entropy, which is sort of the expected value of the amount of information you receive when you resolve what the value of the random variable x actually is. Okay, so in the case that they're all equally probable, the expected value is really pretty simple because all the probabilities are the same, and you just sort of do that little summation and you come up with a number. So this is a very magic number. This basically gives you sort of a minimum amount of bits that I need to send to resolve the uncertainty represented by this random variable. And if I send you more than those bits, I'm being inefficient. And if I'm sending you fewer than those bits, that number of bits on the average, then I'm not giving you enough information to resolve the uncertainty I'm hoping to resolve. So for example, in the choice of 1 of 8 choices, if I only send you 2 bits of information, there's no way I can encode everything I need to code so you know exactly which 1 of 8 choices I had. And I simply haven't given you enough information, enough bits for you to resolve that. So you go, okay, so this is more sort of noodling away, but suppose I gave you some idea here. Suppose I had a set of 8 choices. Okay, so I have, choices 1 through 8. So 7, 6, everything else fits in there. And I send you a message that basically says, look, it's greater than 5. One of the choices, I'm going to give you a message and say, the choices has an index greater than 5. Now, I haven't resolved all the uncertainty, right? You still don't know whether it's 6, 7, or 8. But I certainly resolved some of the uncertainty. You used to have 8 choices, and now you only have 3. So I clearly sent you some amount of information, and we're going to basically use the same basic idea to compute the amount of information that I have given you, okay, by looking at, if you will, the remaining uncertainty, or in this case, the probability that the choices, if they were originally equally probable 1 through 8, the probability that the choices were 6 through 7 is the remaining uncertainty after I've told you that the index is greater than 5. So we can sort of generalize this. If you have n equally probable events to start with, and I send you a message that reduces that n down to a smaller number, m number of choices that are left, okay, I can compute the amount of information I've given you as the log base 2 of n over m. So here I am, I'm going to say, okay, here's some examples. If I'm going to flip a coin, originally there were 2 choices, heads and tails. If I flip a coin and I say, and I tell you it was tails, when I say tails, how much information did you get? Well, you had 2 choices. It's been narrowed down to 1. So I've given you the log base 2 of 2 over 1 bits of information, or in this case, 1 bit. Intuitively, is that satisfying, 1 bit? Well, suppose I had to encode my choice as a digital message, as a binary message, and send it to you. Could I do it in 1 bit, the result of a coin flip? And the answer is, oh, yeah, Chris, come on, ask me a hard question, will you? So I could, I could say 0 with tails and 1 was heads, and when I said a 0, you'd say, oh, that's tails, or so forth and so on. So there's sort of a relationship between the amount of information and hopefully a way of building a code that will transmit that message efficiently. How about if I have a red die and a green die, so the 6-sided with the numbers 1 through 6 on each one, in terms of the number of dots, I roll them. There's 36 possible outcomes, and I tell you what they are. The red die was 3, the green die was 4. How much information have I given you? Well, I've resolved 36 choices down to a single choice, and that's 5.2 bits if I use Shannon's formula. Tell me about 5.2. Anybody bothered about 0.2 of a bit? Do you see yourself sitting with scissors at home, taking a bit and carefully cutting off, a fifth of it and saying, okay, that's my message? What's the 0.2 telling me? Give it a whirl. Yes, sir?
Somewhere between 5 and 6 bits, so you would have to actually use 6 to code all these.
Right, so if I were actually going to send you the information about 1 roll of die, I'd have to send you 6 bits, because I can't really send a fraction of a bit. So that's one insight. But that 0.2 is sort of telling you something. Yes?
With a more complicated encoding message that actually would allow you to have 5.2 bits on average.
Right, so this tells me sort of, on the average, how much information I need to send. Suppose I had to encode 10 rolls of the die and come up with a message that told you 10 outcomes. Right? Well, if I was using 6 bits for each of the messages, I might have to send you 60 bits. This suggests that I might be able to find a different encoding for those 10 outcomes that was closer to 52 bits. Right? And you'll see that sort of theme crop up again. Okay, learning that a card is drawn from a fresh deck, that it's a club. So there were 52 cards. Now there's 13. The thing I'm holding in my hand is one of 13 cards because I've told you it's a club. I've resolved log base. I've given you 52 over 13, log base 2 of that. So that's 52 over 13 is 4. Log base 2 is 4 is 2. 2 bits. Is that a satisfying answer? Well, how many different suits were there? Well, there were 4 suits. Okay, and clearly if I was just interested in encoding the suit, I could do that in 2 bits. 2 bits allows me to encode all possible combinations of, or all possible alternatives of the 4 suits, right? So this formula seems to be, you know, intuitive, right? And so you can think of this as sort of a lower bound on what we hope to be able to achieve with our actual encodings. So this is an abstract measure of how many bits I need to sort of tell you about some event that's happening in the world to resolve some uncertainty. And our goal will be to come up with encodings that come as close to this lower bound, this entropy bound, as we can.